Welcome to this explainer. Today we're diving deep into the dense pages of the ASME Boiler and Pressure Vessel Code, specifically looking at Section V. Now, if you're involved in industrial non-destructive testing, you already know that interpreting a radiograph is way more complex than just holding a piece of film up to a light. We're going to break down the exact code-mandated workflow you need to accurately interpret industrial radiographs. So let's get right to it. Here's our roadmap for today. First up, we'll cover the fundamentals of RT procedures. Second, proving image quality. Third, source and film alignment. Fourth, the actual film interpretation tutorial. And finally, documenting the final verdict.
All right, Section 1, Fundamentals of RT Procedures. Let's lay the groundwork.
Before evaluating literally any weld, you fundamentally have to understand geometric unsharpness. Think of it like a physics reality check. The geometry of your source to film distance actively dictates whether you're looking at a true crisp flaw in the metal or just a blurry illusion. The code relies on the distance from the radiation source to the object divided by the distance from the object to the film. If your geometry is off, your unsharpness goes way up, and your ability to spot those critical defects, well, it practically vanishes.
So, here are the absolute non-negotiables for your setup. The ASME code requires you to strictly follow a written procedure detailing these exact parameters. You simply cannot wing it. You have to document the exact material type and thickness, whether you're using an isotope or an X-ray machine, the precise source-to-object distances, the specific film brand, and the exact screens used. If these aren't locked in from the start, any interpretation you make later is legally invalid.
Moving right along to Section 2, Proving Image Quality.
This is probably the most crucial question an inspector can ask themselves. How do we actually know the film itself is reliable before we even try to interpret the weld? I mean, if the film quality is compromised by bad processing or poor exposure, your whole inspection is basically a wild guess. We have to prove its reliability, and we do that using hard, measurable data.
And the code provides that hard data through density limits. It is incredibly strict here. Your maximum transmitted film density absolutely cannot exceed 4.0. Whether that's for single or composite viewing. And on the lower end, your minimum density has to hit 1.8 for an X-ray source or 2.0 for a gamma ray source. Why is this such a big deal? Because if you fall outside these boundaries, the visual contrast is just too poor to evaluate accurately. The light either can't push through the dark film or the film is so washed out that it hides subtle cracks. To absolutely guarantee our sensitivity, we use image quality indicators or IQIs. Take a look at the required equivalent hole type sensitivity in this table. Based on the hole type designation on the left, you actually have to be able to visually identify the corresponding 2T, 1T, or 4T holes right on your radiograph. If you can't see the designated essential hole, your setup simply isn't sensitive enough to catch tiny, critical defects in the actual weld. The verdict? You gotta reshoot it.
Okay, Section 3, Source and Film Alignment.
Check out this sketch, because it perfectly illustrates why source-to-film alignment matters so much. Notice the radiation source positioned at the top left, aiming down toward the casting body and flange. Now look closely at that shaded triangular region directly behind the flange corner. As an inspector, you have to recognize this blind spot. Since radiation travels in straight lines, the thicker geometry of the flange literally blocks the rays from effectively penetrating that specific wedge of the casting. Your film just can't capture radiographic coverage there. If you don't map out your blind spots, you might pass a part that's hiding a massive defect right in that shadow.
This geometric limitation compounds even further when you're dealing with an unflanged port. Look at how, if the source is positioned directly below the flange, as shown by that sunburst icon, and the film is placed inside the port, the radiation has to pass through a highly angled, extremely thick section of the casting. That shaded, stippled area on the right, that represents another critical wedge where you are flying completely blind. The physics of the beam just won't give you a readable image in that specific zone. Again, you've got to map these areas out in your standard shooting sketches.
Now, it's not just about blind spots, right? It's also about scatter. As radiation passes through heavy metals, it scatters. It bounces around, fogs up the film, and totally ruins your contrast. To fight this, your setup often requires masking material. As you can see illustrated here, a blocking material is placed strategically beneath the flange. This actually stops secondary, scattered radiation from wrapping around and hitting the back of the film. Controlling that scatter is an absolutely fundamental requirement if you want a clean, interpretable radiograph.
Which brings us to Section 4, Film Interpretation Tutorial. This is the main event.
You might think interpretation is mostly just having a good set of eyes, but nope. Your environment is just as strictly regulated as the exposure itself. You literally have to follow these instructions exactly. First, make sure you have subdued background lighting. Glare on the monitor will completely wash out subtle indications. Second, use a calibrated densitometer to mathematically verify you hit those 1.8 to 4.0 density limits we talked about earlier. And third, you have to use an optical magnifier, typically 5x to 10x magnification, equipped with a graticule scale so you can accurately measure the size of a defect right there on the radiograph.
Here's a crucial point. Before you ever reject a weld for a crack or porosity, you have to act like a forensic detective and rule out false indications. A dark line on the film might just be a scratch or a crimp from mishandling. A weird, suspicious blob could be a chemical stain or even a literal fingerprint smudge. You can actually even get false indications from defective intensifying screens inside your cassette. You have to definitively prove the indication is in the metal itself and not just human error from the darkroom.
And finally, Section 5, documenting the final verdict.
An interpretation is completely useless unless it is meticulously documented. The ASME Code demands a rock-solid, comprehensive trail of evidence. You have to maintain the standard shooting sketches we looked at earlier. You need all layout details, the actual radiographs, and a crystal-clear disposition for every single piece of film. Accept or reject. And if it's a reject, you can't just write bad. You must document the specific cause. Was it shrink, gas porosity, a lack of fusion? And to cap it all off, it requires the official signature of the qualified radiographic interpreter.
So why is all that paperwork so unbelievably critical? Well, because of this exact mandate right here from the code. Ultimately, the manufacturer bears the final responsibility for the acceptance of these completed radiographs. They are taking on the liability to ensure that the review, the interpretation, and the evaluation fully comply with the strict parameters we've been unpacking today. The paperwork is what proves that compliance.
At the end of the day, quality in equals quality out. Interpreting a radiograph is so much more than just looking at shadows. It's the culmination of precise physics, strict procedural discipline, and incredibly methodical evaluation. The next time you step up to that light box, ask yourself, does every single step of your process truly hold up to the rigorous scrutiny of the ASME Code? Because in the world of non-destructive testing, your signature isn't just paperwork, it's the final word on human safety. Thanks for joining me on this